Hello, and welcome to the AI Research Roundup. I'm your host, Alex, and today we're diving into some interesting developments in AI. We'll be looking at a paper called SVDQuant Absorbing Outliers by Low-Rank Components for 4-bit diffusion models. Now, diffusion models are fantastic for generating images, but they are often quite large and slow. This paper tackles that by trying to shrink them down using 4-bit quantization. The core idea here is a new method called SVDQuant. Instead of just shifting around problematic outlier values like older methods, it actually absorbs them using a special low-rank component, making the whole quantization process smoother. Okay, so figure 1 here really gives us a visual comparison. It shows images generated using different models and quantization methods side by side, along with performance stats. You can see examples like a cyberpunk cat from the Flux.1 model and a steak photo using PixArt Sigma. Comparing the original high-precision versions to the 4-bit quantized ones, you'll notice the SVDQuant INT4 images look remarkably close to the originals. Much better than, say, the naive INT4 method, which shows clear quality loss, especially in the steak image. And the numbers next to them show SVDQuant achieves significant memory reduction and speed up while maintaining that visual quality. Right, so building on that idea of handling outliers, figure 3 here gives us a more detailed look at the actual SVDQuant process. Initially, you see in part, both the activation X and the weight W have these spiky outliers, making them tough to quantize down to 4 bits directly. So the first step, shown in, is smoothing. This cleverly shifts the outliers from the activation, making it smoother and easier to quantize. But it pushes those outliers into the weight W, making it harder. Then comes the core SVDQuant step in. It takes that difficult weight matrix and uses SVD to split off a low-rank part. This part captures those big outlier values and runs at 16-bit precision. What's left behind is much smoother, and that gets quantized to 4 bits easily. So it tackles the difficulty in both parts. Okay, so while that low-rank SVD component we just talked about is great for accuracy, running it separately at 16 bits could actually slow things down because of extra memory access. Figure 6 here tackles exactly that problem. Part shows that naively running the low-rank part adds a significant latency overhead. You see those extra yellow and red bars for the projection steps. But part shows their solution, the Nunchaku engine. It cleverly fuses the low-rank operations with the 4-bit ones, sharing inputs and outputs. This cuts down that overhead dramatically, as you can see in the Nunchaku bar on the left, much faster. So we saw how the Nunchaku engine cleverly fuses operations to maintain speed. Figure 7 here really provides more visual proof of the quality SVDQuant achieves across a wider range of models and prompts. We're looking at Flux.1 again, but also PixArt Sigma and SDXL Turbo. Compared to other methods shown here like NF4 or VDQ, well, SVDQuant's 4-bit results consistently look much closer to the original 16-bit images. For example, look at the Flux.1 dinosaur-style prompt. NF4 produces an actual dinosaur, while SVDQuant correctly interprets the style. Across the board, really. The SVDQuant images just show better detail and text alignment than the other quantized methods presented. Okay, so we just saw how good the images look with SVDQuant. Figure 8 here gives us the hard numbers on memory and speed, specifically for that big Flux.1 model. Part shows the model size dropping dramatically with SVDQuant INT4, down to around 6 GB from over 22 GB. And part shows similar savings for memory during inference. Then parts and show the speedup. On a desktop 4090 GPU, it's about 3 times faster than the NF4 baseline. But look at the laptop 4090. It's over 10 times faster. That's because the SVDQuant model fits entirely in GPU memory, avoiding slow offloading. Building on those impressive Flux.1 speed and memory results, Figure 17 here looks at another practical aspect, which is compatibility with LoRa's. These LoRa's are often used to tweak models for specific styles. What we see here is that when you apply various LoRa's like realism, Gibbsky, anime, even yarn art to the SVDQuant INT4 model, well, the image quality stays remarkably close to the original 16-bit model using the exact same LoRa. This shows the SVDQuant approach integrates smoothly with these common adapters without messing up the intended style or quality. So, being compatible with LoRa's really shows how practical SVDQuant is. Overall, this work tackles a major challenge, bringing these huge diffusion models down to 4 bits while keeping the image quality high and significantly speeding things up. This really opens the door for running powerful generative models on consumer hardware, which is a big deal. Well, that's all for this episode. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex, signing off.